So, the cosmic distance ladder. What is it? Let's find out. So, basically, we like to know how far away things are in astronomy. That's like a thing that is naturally something that we would like to know if we're looking at something. How far away is it? However, we can't exactly take a tape measure to it. We have to find other ways of figuring out distances. The cosmic distance ladder is a quite important concept because it talks about the different ways that we figure out distance. And the reason we need different ways is because certain ways only work for certain distances. So for longer distances, we need new ways, and they kind of build off of each other. So I'm going to talk about some of the major ways that we use, starting at Earth. And as I go out, I'll be talking about methods that are used to measure distances that are further and further from us on the cosmic distance ladder. First step is parallax. Parallax is a concept in geometry, basically, where the position of something will appear to change if you look at it from two different positions. An easy example of this is if you hold your thumb out in front of your face and then close your eyes one at a time and alternate back and forth, left, right, left, right. You can see the position of your thumb appear to change. Now, it's not because you're actually moving your thumb, it's because your two eyes are in two different positions relative to your thumb. They're both seeing it at a different angle. So, they see it in different positions. We can use the same concept with certain stars. You know, if here's the sun, and here's the Earth going around it in its orbit, make that a little bit nicer of an orbit. You know, and then here's a star. If we look at the star when the Earth is here on its orbit, then we're kind of looking at it in a line like this. And if we're looking at a star when the Earth is here, then we're looking at it with a line like this. Much like how we were looking at the thumb appears to move when we look at it from the two different angles of our two different eyes, this star will appear to move when we look at it at opposite times of the year. And by looking at the amount it appears to change, the angle by which this appears to change, we can use geometry to construct triangles and figure out this distance based on, we can use trigonometry basically. Using this angle and this distance, we can figure out how far away the object is from us. Parallax is a very solid way of figuring out distances. However, in order to use it, we have to be able to see the difference in angle at the two times of year. And that only works for stars that are fairly close to us. You know, I mean, we've gotten pretty accurate, and we can see parallax from stars that are pretty far away, very, very slight. But not even stars that are on the other side of, like, the Milky Way from us, our own galaxy, have too small a parallax for us to use this method. So other galaxies and stuff is certainly right out. So, parallax, we've got our first method. So, I am drawing a blank. I'm drawing a blank on what the next method is. I'll be right back. I'm sorry. Alright, the second method, which I solely forgot, I didn't forget it, I just thought that there was another one between parallax and this, and there wasn't, is the next rung on the ladder are Cepheid variables and RR Lyrae stars. These are two special types of stars with two special properties. Cepheid variables are stars whose brightness, whose luminosity changes over time in a consistent, very mathematically predictable way. Something like this. And the cool thing about it is that their brightness, like their temperature and stuff, affects the period, the rate at which their luminosity goes up and down in time. Some of them, their luminosity changes from brighter to dimmer quickly, and some of them do it more slowly. And if we look at a Cepheid variable star for enough time, and see how quickly it changes from being bright to dim, then we can use that information to figure out how hot it is and how bright its brights are, because that's what controls the period of this fluctuation. So from that, if we can tell how bright a Cepheid variable should be, we can then compare that to how bright it appears to be to our perspective, and use the difference to calculate how far away the Cepheid variable is. RR Lyrae stars are similar, except that RR Lyrae stars just pretty much always have the same brightness. So if we find an RR Lyrae star, we know how bright it should be, we can compare it to how bright it appears to be to us, and use the difference to say, okay, that difference must be due to the distance away it is, and then we can figure out how far away it is. And we can use that to measure the distance to that star, and then we can of course think, okay, so these other stars that appear to be near it are going to be roughly the same distance away, right? And we can just generally use these stars to get an idea of how far away various objects are. You know, if these are part of a cluster of stars, we can figure out how far away the whole cluster is by finding just one Cepheid variable or RA Lyrae star in it, which is nice. But sometimes we need to go longer than the distances at which we can see Cepheid variables and RR Lyrae stars. And the next rung is called main sequence fitting. So, recalling the last video, let's recall the Hertzsprung-Russell diagram, the HR diagram. The way that main sequence fitting works is it supposes that we see a cluster of main sequence stars. Clusters tend to be a lot of stars, you know, maybe a few thousand. And so we can assume, probably, that if we have about 1,000 main sequence stars in a cluster together, they're going to have a pretty good distribution of different main sequence spectral types included in there. And so if we were to graph them, on kind of a modified Hertzsprung-Russell diagram where instead of absolute magnitude on the y-axis, we have apparent magnitude, the magnitude they seem to look like to us. We're going to see that they form a shape that's similar to the overall, main sequence. And this is temperature or spectral type, however you want to do it. And we're going to see that they form a similar shape to what we would expect in a normal Hertzsprung-Russell diagram, because, they're normal main sequence stars. However, if we were to compare this to what the main sequence would look like in an HR diagram with absolute magnitude, we would see that it would look like this. Right? So we see it has the same kind of shape, but it's shifted down from where we would expect it to be on a normal Hertzsprung-Russell diagram. And so we can conclude that the difference in how bright they appear to be to us and how bright we expect them to be has to be because of how far away they are. And so by looking at the separation between what we see and what we would expect to see, we can calculate about how far away that cluster is by assuming that it has a normal brightness level. It has a normal distribution of main sequence stars with normal brightnesses for those main sequence stars. That's how main sequence fitting works. The next rung on the ladder are type 1A supernova. In the last video, I discussed white dwarfs. White dwarfs are formed by stars of certain masses when they die. Our Sun is an example of a star that's going to form a white dwarf. However, there is a limit to which kinds of stars can form white dwarfs. And that limit is called the Chandrasekhar limit, because an astronomer named Chandrasekhar derived this mathematically. And he found that the maximum mass that a star can have and become a white dwarf is about 1.4 solar masses. If a star is greater than 1.4 solar masses, it can't become a white dwarf. Instead, it will go supernova and become either a neutron star or a black hole, depending on how massive it is. So, that's kind of a nice thing to know. But there are cases in which there are two stars orbiting each other, a binary star system, something we've discussed in assignments some before, right? But you can have a situation where one star in a binary star system dies and becomes a white dwarf, but the other is still a normal main sequence star. And if they get close enough, it's possible that some of the mass from the normal still main sequence star can get siphoned off of it and onto the white dwarf from the white dwarf's gravity. This happens periodically. It's not common, but the universe is a big place, so it happens enough. Now, if this is happening, and this white dwarf is slowly accumulating mass, stealing mass from its other partner star, what happens when the white dwarf steals enough mass to become more than 1.4 times the mass of the Sun? Right? It wasn't that originally. If it was more than that originally, it would never have been a white dwarf in the first place. But now it's become a white dwarf and is getting more mass. Well, once it hits this mass, once it hits the Chandrasekhar limit, it immediately goes supernova, right? It is now beyond the point where it can continue to be a white dwarf, and it becomes a supernova. The convenient thing is, it always happens at precisely that point. We know exactly what mass a white dwarf stealing material from its binary partner goes supernova at. And that means that the brightness of those supernova are always exactly the same, because they happen at the exact same point in the white dwarf's development. These are called type 1a supernova, and they are hugely useful because we know exactly how bright they should be, and they're really, really bright. We can see individual type 1a supernovae in other galaxies, right? It's just one star in those other galaxies, but it's bright enough that we can clearly see it all the way here from a different galaxy. It's wild. And because we know exactly how bright it should be, again, we can compare it to how bright it appears to be, and use the difference to calculate how far away it is, how far away the galaxy it's in is. Pretty cool. And then the last link on the cosmic distance ladder that I'm going to discuss, mess that up a little bit, it's the use of Hubble's law. Hubble, namesake of the famous Hubble Space Telescope, was an American astronomer from like the 20s, and he figured out that the universe was expanding. Space itself gets bigger over time. And because the space itself is getting bigger, it's sort of getting bigger at every point, if that makes sense. So Hubble realized that he was looking at distant galaxies, and he saw them redshifting. If you recall the Doppler effect causes a redshift in light when the thing that is emitting the light is moving away from us, if it has velocity away from us. And Hubble noticed a redshift in distant galaxies, and he noticed that the further away galaxies were, the more redshifted they were. So, from that he concluded that the universe must be expanding in size, and also, galaxies that are further away are receding from us faster, because more space is expanding between us and them. And he formalized this in Hubble's law. And so, if we can look at a galaxy, some far-off galaxy, we have an expectation of roughly what the spectra of that galaxy is going to look like. And so, using that expectation, we can look at how redshifted the galaxy is to figure out how quickly the galaxy is moving away from us. And if we know how quickly the galaxy is moving away from us, we can get an idea of how far away it is based on Hubble's law. So that's the last rung in our cosmic distance ladder. Now there is one more important thing about the cosmic distance ladder, why it's called a ladder. We use this metaphor of climbing from one rung to the next for a very specific reason, and that is that each of these steps is based on the previous step in some way. Right? We take our idea of how far away certain stars are based on parallax, and we extrapolate that to get an idea of how to properly interpret the differences in brightness that we see with Cepheid variables and RR Lyrae stars. We estimate these in part based on our estimation of this. And the same is true. Main sequence fitting is the distances we get from that are in part based on the distances we get from this. and the distances we get from type A supernova are based on the distances we get from main sequence fitting. The problem with that is that none of these methods are perfect. They all have inaccuracies, inconsistencies that can get in. Parallax has them, every step has them. But if this step is based on the previous step, then this step isn't only uncertain, it's not only inaccurate because of its own inaccuracies. If we're basing it off of what we know about the previous step, it also inherits the previous step's inaccuracies as well. Because any inaccuracies in this get factored into the assumptions we make to use this. And then main sequence fitting, therefore, in addition to its own inaccuracies, inherits the inaccuracies of Cepheid variables and the inaccuracies of parallax. And type 1a supernova inherit the inaccuracies of main sequence fitting and Cepheid variables and parallax. So with each step on the ladder, we get less and less certain. They become a less precise, less reliable way to estimate distances. Which is a shame, but it's also the best we've got. So, we make it work. But that is an important concept to remember about the cosmic distance ladder. And I believe that about covers it for this week.